So, hello everyone. Welcome to the week 4 NPTEL TA Live interaction session for the Rapid Manufacturing course. The course ID for this course is noc22-me74, and this is Palkin Gupta, PMRF scholar and a PhD student at Department of Material Science and Engineering, IIT Kanpur. The course instructors for this course are Professor J. Ramkumar and Professor Amandeep Singh, Department of Mechanical Engineering, IIT Kanpur. So let us begin with the contents of week 4. So till now, we have been seeing rapid manufacturing, various design processes, modular design concepts, and the various technologies are related to rapid manufacturing like additive manufacturing and all. So now it is time that we compare the rapid manufacturing with the conventional methods that are the subtractive technologies or the CNC technologies that were present there before uh, rapid manufacturing or additive manufacturing came into existence. And in this week, apart from this comparison, we have gone through reverse engineering concepts and its applications and the hardware that are used to implement the reverse engineering technique. So today, we'll start with discussing the benefits of rapid manufacturing and its comparison with subtractive manufacturing. So, as the name suggests, rapid manufacturing is rapid in nature. That is, it reduces the product cycle time. What is product cycle time? The time that the product takes from the development, its inception, to its delivery to the customer. So, that is what is product development time. So, with the advent of rapid manufacturing, because of the reduction in number of process steps and tooling stages, we could have earlier delivery of products to the customers. So, the whole process of product development has speeded up, and because of uh, the rigorous use of computers. The rigorous use of computers and related technology have speeded up the process. Now, here, 3D CAD is used as the starting point, making the data conversion and interpretation easier. So, 3D CAD models that are computer-aided designs, they are used as the starting point. So, this is a data readable by the machines and the systems, and it can be easily converted and implemented to the concerned machinery. So now 3D CAD is what we can see is what you see is what you get. Okay, because what CAD model or what geometry you are actually seeing on your computer screen is what you will be getting after manufacture. Now, on similar terms, we can say that this rapid manufacturing is what you see is what you build. So this means that there are no restrictions to the kind of geometries that can be developed or processed using rapid manufacturing. So, and one of the major advantages of rapid manufacturing is that it reduces number of process steps. So this is one of the major advantages of this. So it is majorly a single step process, whereas subtractive manufacturing they are multi-step processes. So how is it a single step process? Since there is addition of material, you can actually add material. Uh, sorry, since there is addition of material, you can add material in a single step, be it the presence of cavities or internal cooling channels or anything. But when you are going through a conventional process, then you need to always kind of change the orientations if the cavities are on the different surfaces. So you need to just unscrew or remove your product from the jigs and fixtures and then reorient it as per your needs to expose the required surface for drilling or cutting purposes. And here, complex geometries can be performed in a single step. This is what is important. So complex geometries are really easy using rapid manufacturing and they can be done in a single step. Now, coming to the subtractive processes, they require multiple and iterative stages. Okay, so multiple and iterative stages. So, for example, before actually going to the cutting or any drilling process, you need to smoothen out the surfaces. For example, smoothing of surfaces, or you can say flattening. Okay, so and then you go on to drilling on one face, and then cutting on the second face, and then cutting on the third face. Like that, it happens. Now, addition of feature increases the number of stages dramatically. Suppose you had this cuboidal block. Okay. Initially, you had to drill a hole on this surface, or say make a hole here through hole. Now you have to add another groove here. Suppose now you need one groove here, extra groove here. So what happens is now your tool suppose cannot move to this position because of the constraints of the spindle. Tool cannot directly move here. This is just an example, okay? So now what you will do is you will just remove this from all the jigs and fixtures that it is placed in, and then you rotate this geometry in this and then place it with this surface towards your tool. This is your tool, okay? So this has done what? This has increased your step. This has increased one of the processing stage. Now, even a simple change in design results in a significant increase in time required to build using conventional methods. So, why is this significant increase? This is because of the tooling requirements, change of tooling, removal from jigs and fixtures. This time is lesser in case you have used a modular design. If you have used modular design for your tooling and jigs and fixtures, then this time requirement is lesser. Okay, so these were the benefits of rapid manufacturing and the like disadvantages kind of subtractive processes. Now, as a technique, what are the core differences? So, in conventional manufacturing or subtractive processes, you start from a block. So, this is your block of material, and this should be at least as big as your finally required product. Suppose you require any structure which is of 1 centimeter by 1 centimeter and by 1 centimeter, then this starting raw material should be at least of that dimensions. Now, after milling, turning, grinding, or water jet cutting or sawing, these are all subtractive operations. Subtractive means that is removes material by physical or chemical processing. Okay. So, like water jet cutting, that removes material by having water jets. So, by that process, removal of material, you have your final part. But this is rapid manufacturing or additive manufacturing. So what you start from is you start from powder. This is your raw bulk powder. Okay. Or you can have certain filaments as well. Or you can have this raw material in the form of liquid slurry as well. These are the available options. Now, in this case, it is a raw powder. So now what this additive technique will do is it will just slice this CAD model into numerous layers of a uniform thickness and go on to depositing over one another. So this is additive in nature. That is, addition of material takes place layer by layer. Now, how is RM more effective? Okay. So, in rapid manufacturing, we can actually predict the amount of time that is required to fabricate models. Okay, how is that predictable? Because whenever we go on to manufacture a product additively, the machines or the softwares they are now capable enough to allow us to have an estimated time, not the exact actual time, but an estimated time. Now, subtractive conventional method requires skilled craftsmen. Okay, so for performing milling operation or say using a lathe machine for performing milling or turning, you need skilled labor. So they should be knowing how to move in X direction or Y direction or Z direction. Okay, so that knowledge should be with them. And then using that knowledge they need to plan the process and approach the problem in a sequential manner. So suppose there are three holes to be drilled, so which one to drill first, which to be done second, and which to be done third. Okay, and suppose there is a turning operation, so suppose you have to cut steps in a cylindrical job. So the labor should know that he has to first how to generate these steps. Like first he'll make the entire bar for this higher diameter, then just cut out the second higher diameter, this till this particular length, and then go on to this. And what an unskilled labor can do, he can just directly go on to thinning this uh, till here, then retract the tool and then go here and then again retract and do this. So that is not how things proceed. This will create a lot of stresses on the tool. He should know how to plan the process. So rapid manufacturing simplifies this since it is a uniform addition of materials. It is just discretizing the entire 3D geometry into 2D surfaces. So it simplifies the process and that too is done by the software. And it is possible to develop vast range of products with the aid of supporting technologies such as silicon rubber molding, drills, polishing, grinding, etc. Okay. So using these additional supporting technologies, we can have another vast variety of products with us as well. So moving on to the comparison at different parameters for between rapid manufacturing and CNC machining. Okay. So for the materials part, rapid manufacturing was primarily developed for polymers, waxes, and paper laminates. Okay. So it was primarily developed for polymer, waxes, and paper laminates. And with the advent of time, composites, metals, and ceramics can also be processed using this technology. Whereas, on the other hand, CNC machining or in soft materials, medium density fiber boards or machinable foams, sorry, machinable waxes, polymers, they can be processed. And in case of having final products, hard and brittle materials like steel and other metallic alloys, they are processed really fine. They give us homogeneous parts with uniform properties. Whereas we have kind of anisotropy and voids in case of rapidly manufactured products. This anisotropy is, as we had discussed earlier, because of the layer-wise setup along the z direction. So since the resolution is not the same along x and y, and there is a stacking along the z direction, so we have anisotropy and voids. Okay, so the next one was on the basis of speed. So we know high-speed CNC machining is there, and it can remove material really fast from a block. Then, uh, mm, then the rapid manufacturing can add. Okay, so if rapid manufacturing is taking say 5 hours to add a certain height, say 5 centimeter of material, then CNC machining can just remove it within seconds or minutes. Okay, so that much is the time difference in single interaction or a single stage. But if we go on to check the entire product development stage, we see that rapid manufacturing consumes a lesser time. Why? Because it is a single stage process. It is only this stage that is there, and only this time that is takes. Okay, and also multiple parts can be batched. So if you have, suppose this is your build platform, so you can place multiple parts of different geometries on this. Okay, so and they can be processed all simultaneously. Whereas in CNC machining, multi-stage processes are required. So you require multi-stage processes that requires a repositioning, a relocation of parts, and recalibrations of coordinate systems. Okay, and the finishing operations that are performed using CNC machining, they take a lot of time. They can take the time taken by them can vary from days to few weeks. So for finishing of dies, it can take literally take up to 30 days or month or 1.5 months or so. So that much is the time that a CNC can take. So we must not check the interaction at a single part level, but actually check the interaction of the entire product development process. Okay. And now the third part point for comparison is the complexity. So in rapid manufacturing, we had been pointing out this again and again that undercuts, internal features, they can be built very easily, and higher the complexity of the geometries, greater will be the advantage of the rapid manufacturing process. Now, on the other hand, when it comes to CNC, since the tool is mounted on a spindle, so you cannot expect the tool to just to make a curve around the workpiece and go to the bottom part. So suppose this is your workpiece. Okay, here is your tool. This is your tool, and you need some channel here at the bottom here. So you need suppose this to be cut. So this tool cannot just come from here to here, be it 5 axis or 6 axis, and do the machining. You need to remove it. You need to reposition the tool. You need to relocate it and recalibrate it, and then only can this be done. When it comes to the upper surface. Okay. So these are certain accessibility constraints that the tools face in CNC machining. Okay. So uh, um, in such a case, rapid manufacturing comes in handy. Then we see certain parts need to be broken into components and reassembled later. Okay, so certain, suppose you have this example had been given in lecture as well. So suppose this is a cube and you want a channel within this cube which goes from here like this, and it has some bends and goes like this. So this cannot be manufactured directly. So this tool cannot just, it can make a cavity till here, but what about this horizontal part? That cannot be done using this. So what you need to do is you need to break this into two halves, machine the two surfaces, this cavity in two parts, and then assemble it using bolts or screws, whatever, at a later stage. Okay, so that is where the disadvantage of CNC is. Whereas this can be processed in a single step using RF. Okay, now next is the accuracy part. So, RM machines have resolution of a few tens of microns, and this resolution varies along the three orthogonal axes. Okay, because of the layer-wise setup. So, along the Z direction, this is restricted by the layer height, and in X and Y direction, this is usually determined by the mechanism that is being used to develop the 3D printed parts. Okay, so for example, if laser is being used, then the laser diameter governs the resolution. Okay, now in case of CNC machining, this is more of determined by the positioning resolution and the diameter of the rotary cutting tools. The larger the diameter of the cutting tool, lower will be the resolution, or uh, poorer will be the resolution, and smaller the diameter of the rotary cutting tool, higher or the better will be the resolution, as it would then get into the finer details of the geometry. Okay, so it is governed by the diameter of the rotary cutting tool. Now, certain internal features are governed by the tool geometry. For example, you need to develop internal corners or grooves, then they are governed by the tool geometry. Okay. Now the last part is the geometry. So in rapid manufacturing, the 3D geometry is broken into slices or in 2D segments, cross sections of nominal and uniform thickness. So suppose this is a cube, and this will be divided into these thicknesses all along the height. And it is easy to make complex geometries, undercuts, enclosures, sharp internal corners, etc. in rapid manufacturing. Whereas in CNC machining, we need to generate the geometry in 3D, and these surfaces, as in rapid manufacturing were there, we cannot work with those. It is easy to develop simple geometries like cubes, cylinders, etc. But it is difficult to generate free-form surfaces or the complex geometries, because in free-form surfaces, the details are really intricate, so the data points come very close, and that is really not machinable. So, for example, you have some geometry like this. So, to accommodate these curves, the data points will be really close to each other. So these were the differences or the comparison of rapid manufacturing and CNC machining or the conventional machining. Moving on to reverse engineering. As the name suggests, it is reverse in nature. So, what is actual engineering? You have a design in mind, you then go on to developing a CAD model, and then you have the final product. Okay, so this is what is actually forward engineering. So, when you go in a backward direction, that is, you start from the actual part. Okay, you have an actual part. Say, suppose this pencil only. Okay, then you scan it using cameras or 3D scanners. So that camera or 3D scanners will give a data set of the coordinates or the various points in this as per its topology or surface geometry, etc. And then those data points can be engineered and clubbed together to generate the CAD model. So this is really helpful in cases when we have the actual part, but we do not have the CAD models for those, and we need to improvise on them. Say, for example, you have a certain machine and it was built like 50 years ago. That time, these computer generated models were not there. So, what you'll do is you'll just scan it using 3D scanners and have the CAD model instead of just measuring all around and developing by sea. So that would reduce a lot of effort and will give you a more accurate of a model. Okay. So this is really helpful in cases when you do not have the actual CAD models. Really, then actual CAD models or initial models are missing. Okay. Now, so why is it important? So every time we need to improvise on a product or we need to develop or deliver certain updates on a product, we cannot start from scratch. Starting from scratch every time will consume a lot of time. Okay. So, in such a case, we reverse engineer it. Okay. We scan it, get the CAD models, analyze where were the problems, and improvise on them and provide solutions to those problems. And it is an optimization of resources and reduces the overall product development cycle time. Had this technique not been there, then people would have to just drain their brains to get to the actual CAD models just by visualizing the parts and having physical measurements. So, in such a case, this reverse engineering becomes really helpful. Now, so is this even lawful and legal? So, what we see is like we are having a product, we are scanning it and getting the CAD model. It sounds like we are copying the things, but it is legal as far as we are obtaining the products legitimately, and also we are not delivering the same product. Okay, and we are improvising or adding new features to the existing product. Okay, so you reverse engineer a product by say some of your competitor, and you find that oh, there exists certain problem in this. Okay, and then you think of a solution to it and then deliver it to the market. Then it is legitimate and lawful. Otherwise, it is not. Okay, you can just have inter. You can do interfacing using this. You can do interfacing, like take certain features. Suppose A feature from X, B feature from Y, and C feature from Z, and then go on to integrating all three into one. So interfacing can be done. It is used in military and commercial surveillance. Okay, competitive technical intelligence. So getting to know how your competitors are working, getting to know their technical intelligentsia and how is their approach to a problem saves a lot of money and time, and it allows us a product security analysis because after reverse engineering we analyze the product from different aspects. So what is a reverse engineering process? So in this figure we have been describing a reverse engineering process. This is a reverse engineering process. So what we have is we first start from the object or the physical model, actual physical model. Then we scan it using camera or 3D scanner. So this is what is digitization of the object. Okay. So here, what we do is we transform the physical model and get a digital data out of it. Okay, by scan. So we can either have a 3D scanner directly, which gives us the 3D information, or we can have multiple of 2D images from various angles. Okay. And then we can simply club them together or stitch them together into one to get the final 3D part. Now, this data is processed. Okay. This measure data is processed. Surfaces are generated out of these. Okay. So, meshing of this data is done, or these surfaces are generated out of these data points. Because what we have got here is just point data we get. Now here we have to convert this point data into a set of surface data. And then when we go on to developing the final CAD model, we convert this surface data into a solid data. Okay, and once we have this model, this CAD model goes to manufacturing or prototyping. Okay. So, repeating all over again, this forward cycle, in forward cycle, we start from point, like we develop the CAD models, and in that CAD model, we start from points, then lines, then surfaces, and then go to the solid part. Now, in reverse cycle, we have the solid part in the form of this physical model. Step 2, this is step 3, and this is step 4. And from that solid part, we extract the point data. So it is kind of a reverse cycle. Moving ahead, what are the different types of scanners that are available so that we can scan the data? So we have contact-based scanners and non-contact-based scanner. As the name suggests, in contact-based scanners, there is actual physical contact. Actual physical contact between the probe or the tool and the physical object. Whereas non-contact scanners use laser or optics or any kind of signal-based processes and then capture them using sensors to get the data. So in contact scanners, we have coordinate measuring machine based scanners. Okay, so a coordinate measuring machine is the one which just goes on point by point over an object and gives us the information about the x, y, and z coordinates. Now, it is not meant for soft materials. Why so? Because the probe or that is there in these contact scanners that can just leave a mark. Okay. Probe can damage the topological information and lead to faulty CAD models. Okay. And this is a comparatively slow process. Whereas non-contact scanners, they use lasers, optics, or charged coupled devices. So what are they? They capture images by converting photons into electrons. Okay, and the sensor that breaks the image elements into pixels. And using non-contact scanners, shiny surfaces and parallel to light and surfaces that are parallel to light axis cannot be scanned accurately. Okay, so these are the limitations of the non-contact scanners. So in a 3D scanning process, what we first have, it is a five-step process. So first is the acquisition, second is the alignment, third is the mesh generation, and fourth is post-processing, and fifth is simplification. Okay, so acquisition is the fundamental step, and in this step, image is acquired as a set of data points. So this is a fundamental step, and image of the object is acquired in the form of data points. So these points then define a 3D representation of the part of the object that has been framed and hit by the light pattern generated by the projector. Okay, so for example, you are using non-contact based scanner. So suppose this is your laser, then and this is your object. So it will just emit certain waves, and then there will be some reflection from this object, and that data will be captured by the detector unit of this scanner. And based on that data, you will get the data points and the corresponding x, y, z coordinates. Okay. Now comes the alignment part. In alignment, we need to make alignment between the world coordinate system or the universal coordinate system and the user coordinate system so that uh, we can interface between different parts of the same object easily. So suppose we have a big object, say a car. So suppose this is your car. So in one go, you can have In first phase, you can have just overall geometry of the car, and in the second phase, you can have intricacies of the doors, windows, etc. So, so this will be in two different data sets. So you need to align them along the same coordinate system so that they can be clubbed together and further a single CAD model can be formed having a consistent coordinate system. Now, after this, we have to generate the meshes. Okay, so this mesh generation part, what it does is it converts a set of 3D points to a data constituted by a set of triangles, or we can say the mesh. So suppose if this was a cube and in that 3D data, so this surface, this particular surface, this will be converted into a number of triangles. Say two triangles, it will be converted into in the mesh generation part. And a mesh is this is the first useful data that can be elaborated and exported in different formats. By elaborated, we mean we can edit it and convert and add certain more features to it or make some changes. Desired format. Now, second last is the post processing. So, of course, for every operation, every manufacturing operation actually requires post processing for the enhancement and finishing of the mesh. So, this is for enhancement and finishing of the mesh. So, have so as to have a more accurate CAD model. Okay. So, its purpose is to basically prepare a complete and flawless 3D model. All right. Okay, so this can be chosen depending on the results to be achieved or what decisions you make. As per those, it can be selected. And last is the simplification. Under this process, all the steps made on the mesh simplify the data. Okay, so it is basically concerned with mesh definition. What is termed as mesh definition, that is reduction of the number of mesh triangles. Okay. Now, what hardware are required to use for reverse engineering? So mainly we have three technologies: contact, non-contact, and destructive. So contact and non-contact type we have seen very briefly. So in this we have two methods. One is point-to-point sensing and another is analog sensing. In point-to-point sensing, what happens is as the probe touches the surface, its contact with the spindle is left. So touch triggers probes installed on coordinate measuring machines or articulated mechanical arms. Okay, and gather the coordinate points of surface. So as soon as that contact with the spindle is left, it records the data. As contact occurs with model, connection with the spindle is left, and that helps in recording the data. And the other is analog sensing, where scanning probes are installed on the coordinate measuring machines or CNC machines. And what they do is they provide continuous reflection outputs, and these can be combined with the machine position. So to have a universal coordinate system to derive the location of the surfaces and the exact CAD data. Now, in the non-contact method, we have the ones that are reflective in nature or transmissive in nature. So, for reflection, we use the reflective wave, and in transmissive one, we use the waves that are transmitted or that actually pass through. So, it uses EM waves, microwaves, sonar, okay, and all these types of waves. So, in transmissive, we have CTs and MRIs. These are commonly used in medical fields. Okay, so CT scan this provides a large series of 2D X-ray cross-sectional images taken around a single rotational axis, whereas MRI uses radio waves and magnetic fields to scan. Okay, so MRI gives better results and can image the soft tissues of the human body more accurately. Whereas in reflective, we have optical ones and non-optical ones. So non-optical ones obviously uses the microwaves, radars, or the sound. So this is used in basically seas, and this is used in airlines. Whereas the optical ones, they are passive and active. They use different methods. In passive, there are shape from focus, there is shape from shading or the shadows, or shape from stereo, shape from motion, that is any kind of translations or rotational motions. And in active, we have triangulation methods, structured light, time of light, Moire effect, or coherent laser reduction. Okay. So let us move to the question set for this week. Okay. So the first question for this week is: even a relatively simple change in the design may result in a significant increase in the time required to build using conventional methods. True or false? So this is true. We had discussed taking a simple example, which we can take up again. So suppose we have this cube, and there was a channel grooved on top surface of it. Suppose this was the channel to a certain depth that was grooved here. So this was grooved on the top surface. Now, if you add another channel at the bottom surface to be grooved, so now there is a second channel which is to be grooved at the bottom surface. So the tool cannot literally come, and this is your tool. So it cannot move to this location, be it 5 axis or 6 axis with CNC. So it cannot move to the bottom surface. What you need to do is you need to relocate the part, reposition it on the work platform, and recalibrate it as per the working coordinate system, and then only you can uh, cut this out. So this was a simple change in the design, and this resulted in a significant increase in time. Okay, using RM, this would have been done in the single step only, as this would have been given to the CAD, and it would just not have deposited the material here. So the answer is true. Second, including more features in a design may decrease the iterative stages required. So this is false. So taking the example from the previous slide only. So this was suppose this is feature 1, this is your feature 2. So when feature 2 was added, as per previous question, when feature 2 was added, a second iterative stage, say only two stages, and or we can say an additional iterative stage was required. So, including more features in a design actually increases. So it doesn't decrease, it increases the iterative stages required. So the answer is false. Now, third question. Subtractive manufacturing results in less waste generation as compared to additive manufacturing. True or false? So, in this example here, this is subtractive manufacturing, and this is additive manufacturing. Okay. So, in subtractive manufacturing, this entire block of material, this entire block of material has been removed or cut out. Okay. So, this entire block is actually a waste. But in additive manufacturing, in this block didn't contain any material in the first place. So no material was added in this phase. Okay. So when this printer was actually printing, so it just skipped this portion. Sorry, it just skipped this portion and just solidified the parts in the other region. So from top, it is going to look like this. So when printer was printing, say a laser was projecting, so only this much area was exposed to the laser and the material in this area solidified. And the material here is safe and this material can be reused. But this is all in the form of small chips and cannot be reused. So this is waste. So subtractive manufacturing results in more waste generation. So this is false because subtractive manufacturing results in more waste generation as compared to additive manufacturing. Because the whole concept is subtracting the material, and whatever you subtract is waste. Simply, in simple terms, whatever is getting subtracted is being wasted. Okay? Whereas this is not the case in case of additive manufacturing. So moving on to the next question, question 4. Rapid manufacturing can be seen as a way. to more effectively predict the amount of time to fabricate models. True or false? This is true. We have discussed this. So, in rapid manufacturing, when you additively manufacture a product, suppose you are building this cube. The cube is the simplest example, that is why I take this every time. And you have decimated it into a number of layers. So, suppose this one layer takes 1 minute to process. And this approximate time is given by the software as well, based upon the printing parameters that we select. So we know the area in which material is deposited. We know the time to be used for one layer. So we can just multiply it. Suppose there are 20 layers, so it will take 20 minutes. Okay. So this way we can predict it. Okay. Suppose in case of laser-based systems, we can define the laser exposure time per layer. Okay, this is defined by the user. So now, depending on the number of layers, the total time can be predicted. Whereas in conventional, this is not the case because here things very much rely on the hand of the skilled person who is using it and how he plans the process, how he approaches the problem in a sequential manner. Next question. The number of processes and resources can be significantly used when using rapid manufacturing. This is true. So we have seen the advantages of rapid manufacturing where it says it reduces number of steps, uh, specifically in case of complex geometry, wherein these conventional machines require multi-stage processes. So conventional or CNC, they require multi-stage processing. Whereas this rapid manufacturing, this is a single step processing. So the number of resources and processes can be significantly reduced. Next question is, CNC machining requires careful planning and sequential approach that may also require construction of fixtures before the part itself can be made. True. We have discussed this right now. It requires planning and sequential approach. Okay, so suppose again that example. Suppose these steps are to be turned on a cylindrical bar. So suppose this is 10 mm, this is 5 mm, and this is 2.5 mm. So the skilled labor that is using it, he has to decide if he has to cut the smallest first or he has to cut the largest first. Okay, and also sometimes they require the construction of fixtures. Okay, so there can be certain parts that require one kind of fixture along one direction and another kind of fixture along other direction. So this is true. Next question. Rapid manufacturing cannot be used to replace the multi-stage processes. This is clearly false. It can be used. Can be used. We have seen it is really beneficial for complex geometry. It can easily make undercuts, sharp internal corners, internal cooling channels, etc. all in a single step. Whereas in CNC, we require to break that into components and then assemble it later on. Now, next question. CNC machining is primarily a dash process. Additive, subtractive, both additive and subtractive, or none of these. So, CNC machining is a subtractive process. It is a subtractive process. It works on the principle of removal of materials to develop the physical object. Okay, and this removal of material is subtractive. Okay. Next, second last question. Rapid manufacturing technology was originally developed around polymeric materials, waxes, paper laminates, or all of these. We have seen this during comparison, and it was developed for all of these as an initial material. And after these, with the advent of time, it became applicable to composites, metals, and ceramics as well. And after these, it came into existence for ceramics, metals, and composites as well. Okay. Now the last question for today: which of the following materials can use CNC? Medium density fiberboard, machinable foam, machinable waxes, or all of these. So all of these can use CNC machines. Even the hard and certain brittle materials like steel and other metallic alloys give very fine results when processed through CNC. So these were the questions for today. So I hope the content was clear. If you have any doubts, you can raise them up, or you can always post them in the discussion forum. We can take up questions from there as well. So this video will be uploaded to you, and these PDF or PPTs will be given to you through Google Drive links. Uh, I think we can end the session now, or if there are not any questions. Okay. So thank you everyone. We'll meet next week at the same time to cover the next week's content. Thank you.